Hello student, welcome to the lecture on application of derivatives, and after this lecture we will be able to learn the following objectives. Discuss the determinant of a square matrix, explain the properties of determinants, understand the minors, describe the cofactors, discuss the application of matrices and determinants, explain the adjoint of a matrix, understand the expanding to find the determinant, discuss the inverse of a square matrix, understand consistent and inconsistent system, discuss the system of linear equation. Let us start with the introduction of the application of derivatives. How the derivative can be used: to determine rate of change of quantities, to find the equation of tangent and normal to a curve at a point, to find turning points on the graph of a function, which in turn will help us to locate points at which largest or smallest value of a function occurs. Decreasing function. A function is said to be a decreasing in an internal if f of x plus h less than f of x for all x belonging to the interval when h is positive. We will also use derivative to find intervals on which a function is increasing or decreasing. Finally, we use the derivative to find approximate value of certain quantities.
A piece of pipe is being carried down a hallway that is 10 feet wide. At the end of the hallway, there is a right angle turn and the hallway narrows down to 8 feet wide. What is the longest pipe that can be carried around the turn in the hallway, provided that at any time during the turn, we have to keep the pipe horizontal? The largest pipe that can go around the turn will do so in the position shown in the animation. Let's assume that the length of the pipe in the small hallway is L1, while L2 is the length of the pipe in the large hallway. Now, if theta is equal to 0, then the pipe is completely inside the wider hallway. And we can see that theta tends to 0, then L tends to infinity, which means that if the pipe is completely in the broader hallway and there is no turn, then an infinitely long pipe can be carried through such a hallway. Likewise, if theta is equal to pi by 2, the pipe is completely in the narrow hallway and there is no turn, we can carry an infinitely long pipe through such a hallway. Now here the question is tricking us, so pay attention. The total length of the pipe becomes infinity at both 0 and pi by 2. There is an angle that will minimize the total length of the rod and make it fit into the turn. Actually, all the lengths which we are getting here are the lengths of the rod that don't fit into the turn. The minimum length of the rod that doesn't fit into the turn is what we are after in this problem. Obviously, the minimum length of the rod that doesn't fit into the turn is nothing but the maximum length of the rod that does fit into the turn. So, although the question asks for maximization of the length, the problem is actually a minimization problem. The constraints for this problem are the widths of the hallway. We'll use these to get an equation for L in terms of theta. So, using basic right triangle trigonometry, we can see that L is equal to 8 sec theta plus 10 cosec theta. We'll minimize this new equation, which gives theta is equal to 0.8226 radians. So, if theta is equal to 0.8226 radians, then the pipe will have a minimum length, which is equal to 25.4033 feet.
Let's discuss about the rate of change of quantities. The derivative ds by dt, we mean the rate of change of distance s with respect to the time t whenever one quantity y varies with another quantity x, satisfying some rule y equal to f of x, then dy by dx or f dash x represent the rate of change of y with respect to x, and dy by dx at x equal represent the rate of change of y with respect to x, and dy by dx at x equal to x not represent the rate of change of y with respect to x at x equal to x0. Further, if two variables x and y are varying with respect to another variable t, that is if x equals to f of t and y equals to g of t, then by chain rule we have derivative of y with respect to x as shown on the screen. Thus, the rate of change of y with respect to x can be calculated using the rate of change of y and that of x both with respect to t. Here we will discuss about the increasing and decreasing functions. Increasing function. A function is said to be an increasing function in an interval if f of x plus h greater than f of x for all x belonging to the interval when h is positive. A function is increasing if the y value increases as the x value increases as shown. It is denoted as x1 less than x2 implies f of x1 less than f of x2. A function that either increases or decreases everywhere in an interval is called monotonic on function. Decreasing functions. A function is known as decreasing if y value decreases when x value increases. It is denoted as x1 less than x2 implies f of x1 greater than f of x2. For a function y equals to f of x, w when x1 less than x2, then f of x1 greater than equal to f of x2, then the function is decreasing. When x1 less than x2, then f of x1 greater than f of x2, then the function is strictly decreasing.
In this lesson, we'll take a look at increasing and decreasing functions. So in other words, where is the function increasing, where is it decreasing? And if you take a look at my example here, I have a cubic shaped graph. And the function is increasing as you go from left to right if you're going up. So it's increasing along there. So it also be increasing along here as well. And so I've defined that maximum point to have an x-coordinate A and this minimum point to have an x-coordinate B. So notice that anywhere to the left of A along the x-axis, the function is increasing. To the right of B, or greater than B, the function is also increasing. So I could write those as intervals. It's increasing where x is less than A and also where x is greater than B. Now, if you draw a tangent line in any of those intervals, so for example, if I were to draw a tangent line here, or here, here, or here, notice that all of those tangent lines are sloped upward. So the derivative would be positive in all of those places. So a positive derivative means that the function is increasing. Now the function is decreasing along here between A and B. So the interval was between A and x is between A and B. And notice if I draw a tangent line there, anywhere in there, the tangent line slopes downward. And so a downward sloping tangent line means the derivative is negative. So a negative derivative means the function is decreasing. Now, one last thing here. If I were to draw tangent lines at this maximum point or this minimum point, notice that the tangent line is horizontal there. That means that the derivative is 0 in both of those places. The first derivative is 0. So notice that a function changes from increasing to decreasing where the derivative is 0, or decreasing to increases where the derivative is 0. So setting the derivative to 0 gives you those places where the function might change from increasing to decreasing or vice versa. And we'll use that idea in the example in the next page. So in this example, we're asked to find upon what intervals is this function increasing or decreasing. And we're going to do this without the aid of a graph. So the first thing that I would do is differentiate this function. So the derivative of 2x cubed would be 6x squared using the power rule. Derivative of negative 9x squared would be minus 18x, and derivative of 12x is 12. 2 is a constant, so its derivative would be 0. So I would set that equal to 0. And notice in this equation, the entire equation is divisible by 6. So I can make it simpler by dividing everything by 6 and get x squared minus 3x plus 2 equals 0. So we would try to factor this. I wouldn't bother use the quadratic formula because it factors fairly easily. Look for two numbers to add to negative 3, multiply to positive 2. So that's negative 1 and negative 2. So x minus 1 and x minus 2 would be the factors. So setting each of these to 0, we get 1 and 2 as the places where the derivative is 0. So on my number line, I'll place the 1 and 2. So it's broken the number line or the x-axis down into 3 intervals: to the left of 1, between 1 and 2, and to the right of 2. At 1 and 2 is where the derivative, of course, is 0. And so all we need to do is investigate the value of the derivative, in fact just the sign really, in these 3 intervals. So I'm going to take a number to the left of 1. I'm going to take 0. I could take any number of 1. If I want to take negative 102, I could. But any number to the left of 1 will work in this interval. So we plug 0 in place of x in the derivative. Of course, this part would all be 0, and you would just get 12 for your derivative. Now, it doesn't matter that it's 12. The fact that it's greater than 0 is what's important. So I'll put a plus here to represent it's greater than 0. Now, next I'm going to take a number between 1 and 2, and I'm going to use 1.5, but you could take any number between 1 and 2. If you want to use 1.95, that still works. And we'll substitute that number in place of x in the derivative. And that works out to negative 1.5. It doesn't matter what numerically it is. The fact that it's negative is what's important. So the negative derivative means it's decreasing between 1 and 2. And then I'll take a number above 2. I'll take 3. So I'll put 3 in place of x, and actually it turns out to be 12 again. Just substituting that number in place of x in the derivative. And so it's a positive derivative there, so it's gone back to increasing again. So now I need to state, where is it increasing, where is it decreasing? It's increasing below 1 and to the right of 2. So those intervals would be where x is less than 1 and where x is greater than 2. It's decreasing between 1 and 2. So I would write that as x is greater than 1 but less than 2. Or 1 is less than x is less than 2. That means the same thing. So that's the decrease.
Let's now talk about the first derivative test for increasing and decreasing function. The function f of x is continuous on interval a, b, and differentiable on ab. If f dash of x is positive greater than 0 at every point in a, b, then f of x is increasing in the interval. If f dash of x is negative less than 0 at every point in a, b, then f of x is decreasing in the interval. Increasing and decreasing function graph is: when the function is increasing, the graph of the function rises from left to right. On the other hand, while the function is decreasing, its graph falls from left to right. The function y equals to x squared is decreasing in the interval minus infinity 0 and is increasing in the interval 0 infinity. But the cubic function is increasing in the entire domain minus infinity infinity. From the graph of an increasing and decreasing function, we come to know following things about a function. If the function is increasing to the left and decreasing to the right of a critical point, then the point corresponds to a local maximum. If the function is decreasing to the left and increasing to the right of a critical point, then the point corresponds to a local minimum. If the first derivative is positive to the left and negative to the right of a critical point, then the point corresponds to a local maximum. If the derivative is negative to the left and positive to the right of a critical point, then the point corresponds to a local minimum. If the critical point happens to be an inflection point, then the change in the behavior of the function is not seen. The function continues to be in the state of either increasing or decreasing. The cubic graph has point of inflection at x equal to 0. The graph is seen increasing on either side of the critical point 0, 0. Indeed, the function is monotonic, increasing in the entire domain infinity, infinity. Now let us discuss about the tangent and normal lines. The figure shows the graph of the curve y equals to f of x and p is a point on it. The TPQ is the tangent to the curve at P. This is inclined at an angled f to the positive of x-axis. Look at the screen for the better understanding. The normal line is defined as the line which is perpendicular to the tangent at the point of its contact to the curve. Therefore, the equation of the normal line at P to the curve y equal to f of x will be as shown. Let us now discuss about angle between two curves. Angle between two curves is the angle between two tangent lines drawn to the two curves at their point of intersection. If M1 and M2 are two slopes of these two tangents and is the acute angle between them, then we have theta equal to mod of m1 minus m2 by 1 plus m1 m2. Let C1 and C2 be two curves intersecting at a point P. Then these curves are said to intersect orthogonally at P. If tangents at P to C1 and C2 are at right angles, that is m1 and m2 equal to minus 1. Definition. Let the tangent and normal at P, x1 and y1 to the curve y equal to f of x meet x exits at T and G respectively. Let Pn be perpendicular to the x exits at N. Then PT is called the tangent length at P. PG is called the normal length at P. The segment Tn is known as the subtangent at P, and the segment NG is known as a subnormal at P. Now we will talk about the approximation of application of derivatives. Approximate the graph of f of x by studying only its first and second derivative. Now we will develop further on the definition of the derivative to understand how we can obtain accurate approximation of f of x using its first derivative only. Before continuing, let me address a suspicion that is growing in your mind. You're probably wondering, why do we care about using function derivatives to determine the behavior of the original function? If we want to analyze how f of x behaves, we can go and graph it directly without having to look at its derivative. The antiderivative of the function will give us the exact relationship between the situation and the changing dimension. In order to understand how to define an instantaneous rate of change and then calculate the net change, the relationship between the function and its derivative must be fully grasped. Let us begin with the definition of the derivative. Here dy by dx is equal to f dash x. The derivative gives us the instantaneous rate of change of a function over an infinitely small interval dx. If we multiply both sides by dx, we get as shown. Therefore, this equation only represents an approximation to the net change in over a discrete interval, as it assumes that the rate of change is constant. The approximation gets less and less accurate as delta x increases f. Here we will discuss about the maxima and minima. The derivative provides information about the gradient or slope of the graph of a function. We can use it to locate points on a graph where the gradient is 0. The stationary points of maxima and minima during a graph of a function using a graphical calculator or computer graph plotting package will reveal this behavior. But if we want to know the precise location of such points, we need to turn to algebra and differential calculus. Consider the graph of the function y of x. If at the points marked a, b and c, we draw tangents to the graph, note that these are parallel to the x-axis. They are horizontal. This means that at each of the points a, b and c, the gradient of the graph is 0. Turning points. At points a and b, the curve actually turns. These two stationary points are referred to as turning points. Point C is not a turning point because although the graph is flat for a short time, the curve continues to go down as we look from left to right. So all turning points are stationary points, but not all stationary points are turning points. Point A in the figure is called a local maximum because in its immediate area it is the highest point and so represent the greatest or maximum value of the function. Point B in the figure is called a local minimum because in its immediate area it is the lowest point and so represent the least or minimum value of the function. Distinguishing maximum points from minimum points. The gradient of the graph as we travel to the minimum turning point from left to right, that is, as x increases dy by dx goes from negative to 0 to positive. Notice that to the left of minimum point dy by dx is negative because the tangent has negative gradient. At the minimum point dy by dx equal to 0. To the right of the minimum point dy by dx is positive because here the tangent has a positive gradient. So dy by dx goes from negative to 0 to positive as x increases. Now in the end, let us summarize what we have learned in this lecture. We use derivative to find intervals on which a function is increasing or decreasing. We also use the derivative to find approximate value of certain quantities. The derivative ds by dt means the rate of change of distance s with respect to the time t. A function is increasing if the y value increases as the x value increases. A function is known as decreasing if y value decreases when x value increases. If the first derivative is positive to the left and negative to the right of a critical point, then the point corresponds to a local maximum. If the derivative is negative to the left and positive to the right of a critical point, then the point corresponds to a local minimum. Angle between two curves is the angle between two tangent lines drawn to the two curves at their point of intersection. The antiderivative of the function will give us the exact relationship between the situation and the changing dimension.